Okay, so last lecture today. I know you're all very sad to have the last lecture on probability, but don't worry, you're going to use it next term. Okay, so what we did last Friday was to look at statistics. And we looked at the notion of random samples. So we said we have a random sample, right, made of n random variable. Each of them has a certain distribution, probability density function, right? So you remember this random sample, we have n random variable. They're actually identically independent and identically distributed, right? So each of them has a certain distribution f of x, right? For instance, they can all be normal distributed with a certain mean and certain variance. They can all be exponentially distributed with a certain parameter lambda, right? And so what we were trying to do when we worked on statistics, essentially try to, based on some data, try to build some estimator to estimate the parameter of those distributions. So we may say all those random variables are normal distributed, but I have no idea what's actually the mean and what's the variance. So we have to actually build an estimator, and then usually we denote it with a hat, estimator of a certain parameter theta, right? So for instance, mu hat can be the estimator of mu. You can have sigma hat square, which would be the estimator of the variance. You could have lambda, which would be the estimator of the lambda of the exponential distribution, right? Good. So, so what is this estimator? This is a random variable, right? So the estimator is a random variable. That means actually the estimator can be modeled using probability theory, and that estimator has a certain probability density function. Okay. Good. So how do we construct estimator? Well, to construct good estimator, the first thing we have to do is to identify some properties of estimator, right? So what we did last week was identifying two properties, and we talked about whether the estimator is biased or unbiased estimator, right? So what does that mean? Well, if I have a certain parameter to estimate, let's say parameter theta, and I build an estimator, I construct a certain estimator, theta hat. This theta hat is a random variable, so it will have a certain, let's say, probability density function, right? So let's say something like this, right? And so if this is the PDF of theta hat, if the expectation of theta hat is equal to theta, then we have an unbiased estimator, right? On the other hand, if you have a situation like the following one, you have parameter theta, and you have a distribution that is something like this, right? So in this case, you have expectation of theta hat. This is the distribution of theta hat. In this case, you have expectation of theta hat is different than theta, right? I use square bracket or rounded, it doesn't matter, right? This would be biased, right? So that means actually, if you build this estimator on average, that estimator will not give you the value that you're looking at, or you're looking for. Okay, so the bias essentially is a measure of the difference between the expectation of the estimator and the value that you're looking for, right? And so you want, generally speaking, you would prefer having an estimator that has a zero bias. Good. So what we saw, for instance, last week, we saw that actually if you do a sample mean, so the sample mean is an unbiased estimator of mu, right? So if you look at the mean of a distribution, right? The mean, for instance, of this normal distribution, and then, well, you can use a sample mean essentially as an unbiased estimator of mu. Good. So with this, this is a first property. The second property of estimator is whether there are minimum variance. So you can define the notion of minimum variance unbiased estimator. MVUE. What does that mean? That means that if you have a parameter theta, you build, let's say, two estimators. So I have a first estimator, let's say, like this. And I have a second one, so this is, let's say, theta 1 hat. And I have a second one that is like this. Right? What you have here is expectation of theta 1 hat is theta, expectation of theta 2 hat is still theta. So both of them are unbiased. Right? But what you see is that the variance of theta 1 hat is actually smaller than the variance of theta 2 hat. Right? The distribution of theta 2 hat is essentially wider around its mean. So minimum variance unbiased estimator, it means that actually you choose the estimator among all unbiased estimator. You choose the one that has the smallest variance, right? So in this case, you choose theta 1 hat because essentially it has a variance that is smaller than theta 2 hat. Yes?
This term is used when we have a set of estimators that we come up with. It's not like all of the possible estimators. The one with the minimum variance will be the MPUE.
So this minimum variance estimate is let's say you have different estimators. You have to choose among different estimators, but you all know that all those estimators are unbiased, right? And so the one you would choose, if you use this property, you would choose the one that is that has the minimum variance. It doesn't mean that this is the best estimator. It just means that among the ones that actually are unbiased, you would prefer the one that actually is has minimum variance.
That set of unbiased estimators, is it all possible ones that are unbiased, or just like whatever set we currently have?
Well, let's imagine you have an experiment and you have to build, you have to construct an estimator, and you may have different ways of constructing that estimator. And so you may identify method 1 and method 2. And so you wonder which one among those two is the best. That's what I'm talking about.
And you just call that one the MPUE.
That's right. Okay. So this is nice, but that doesn't resolve all the problems. The reason being that you could have the following situation. You could have a situation where you have a parameter theta to estimate, and you have a first estimator, theta 1, right, theta 1 hat, that is such that expectation of theta 1 hat is different from theta, right? But you have another estimator, theta 2 hat, that is such that theta 2 hat is, expectation of theta 2 hat is equal to theta. So that means actually the red one is unbiased, but the blue one is biased, right? But on the other hand, from this figure, you could say, well, it looks like the variance of theta 1 hat seems to be smaller than the variance of theta 2 hat, right? So in that case, you have one estimator is biased, but has a smaller variance, right? And the other one is unbiased, but actually has a larger variance, right? So in that case, how do you choose the estimator? Well, this is what we can do is to introduce the notion of mean square error, so MSE. And how do you define the mean square error? Is the following. The mean square error of a certain estimated theta hat is given by an expectation of the square of a difference between that estimator and theta, right? So this is not a variance, right? It looks like a variance. It's not a variance. It's not a variance because theta is not necessarily the expectation of theta hat. Yes?
So is it quite possible that your estimators as well would be skewed, essentially? Could you have a skew on the one which has got smaller variance?
What do you mean by skew? In terms of skewness, like the... well, this is just a representation of the PDF. You could have any PDF, right? So this maybe looks like something like more Gaussian, but you could have any PDF, right? So we'll see some example where essentially you can have normal, you can have exponential, but you can have different form. It's just a qualitative way of representing things here. Right, so this is the mean square error. So let's look at what that means. So that's the expectation of the square of the difference between the estimator and theta. So let's expand this a little bit. Let's expand this a little bit. And so I'm writing, I'm subtracting a term here and then adding it. Right, so I'm not changing anything to that definition. But by doing that, now I can actually expand this and see what that looks like. So I have theta minus expectation of theta hat plus expectation of the square of those two plus 2 times the first term multiplied by the second term. Okay, now I can just distribute this inside. I have expectation of theta hat minus the expectation of theta hat square, right? Plus expectation of the square of this plus 2 times the expectation of theta hat minus expectation of theta hat. Multiplied by expectation of theta hat minus theta. Right, what you see here is actually the expectation is only distributed over this term, not this one. This is a constant, this is a constant, this is a constant. Right. So what do we have here? What is this term equal to? I have expectation of theta hat minus the expectation of theta hat. This is equal to 0. Right? We have expectation of theta hat minus expectation of theta hat. This is the same as expectation of theta hat minus expectation of theta hat, right? Good. What do we have here? This, if you look at the definition of bias, we have that, right? So this is what we have here, right? So this is essentially, this term is nothing else than the square of the bias. And what is this quantity here? This is the square of the deviation between the estimator and its mean, its expectation, right? So this is a variance. So this is the variance of theta hat. Okay? So the mean square error is equal to the variance of the estimator plus the bias, the square of the bias of that estimator, right? So here, if you have 2 estimators, theta 1, if you have estimators theta 1 hat and theta 2 hat, well, if you choose that property of MSE, you would choose theta 1 hat if the MSE of theta 1 hat is smaller than the MSE of theta 2 hat, right? So here is a property or metric that actually accounts for both the variance and the bias of the estimator. So in the example we had here, maybe theta 1 is actually biased but have a smaller variance. Theta 2 is unbiased but has a larger variance. By looking actually the MSE, computing the MSE of each estimator, you can actually identify which one has the smallest variance and decide accordingly which estimator would be most suitable. Okay, so those actually three different properties, or three properties, MSE, minimum variance, and the notion of bias and unbiased, three different properties of estimator that actually are used quite extensively to identify or to characterize the performance. Now, what we're going to do next, in the next 25 minutes, is essentially construct estimators using some kind of well-defined methodology. So the question we're going to look at is how to construct estimators. Right, and we're going to look at two different methods. The first one is called the method of moments. And the second one is called maximum likelihood. Okay, so those are two different ways actually to construct estimators. So let's look at the first one. Let's look at this method of moment. So as the title says, method of moments means actually you're going to use some moments. So you remember what a moment is. We looked at the kth moment was expectation of x to the kth, the power k. Right, so you have, if you have a certain random samples here, with k, with n random variables, and each of them has a certain distribution f of x, what we're going to look at is essentially the kth moment of this random variable. So we had the first moment was the expectation of x, the second moment was expectation of x squared, right? So this is essentially what we call the theoretical moment. Right? What else we can define is the sample moment. And the sample moment is essentially 1 over n sum x I to the k. Right? So we have the first moment, I go from 1 to n. We had the first moment was the sum of 1 to n of xi. We can have the second sample moment is 1 over n xi squared. Right? Oops. Apologies for this. Right, so we have sample moment and we have theoretical moment. What we do in the method of moment, we actually equate the theoretical moment and the sample moment. So we construct the estimator by equating theoretical moment with sample moment. What does that mean? So let me give you an example to show you how it works. So let's imagine I have a random sample x1 all the way to xn, and they're all exponentially distributed. Right? And what we want to do is to construct method of moment estimator of lambda. Right? So we're going to denote this lambda hat. Okay? So using the method of moment, how do we do this? We're going to look at the first moment, the first theoretical moment, and equate this to the first sample moment, right? So the first theoretical moment is expectation of x, right? If you have an exponential random variable, what is the expectation of x? Is 1 over lambda, right? We did this several weeks ago, right? So this is my theoretical moment. Right? What is my sample moment? The first moment is 1 over n sum xi. Right? So I will choose here or construct the estimator such that 1 over lambda hat is equal to my sample mean. Okay, so I force the sample moment here that can be actually evaluated based on data samples. I force it to be equal to the theoretical moment, right? And so by doing this, essentially the estimator, the method of moment estimator of lambda would be 1 over the sample moment. Okay? So if you have a data set, right, and you have measured x1 all the way to xn, right? For instance, the values I mentioned earlier in last week, we had like 50 or 48 point something, right? You take n measurement, you have done the experiment, you have n measurement. Well, you can actually construct an estimate. The estimate of theta will be 1 over x bar, where x bar is nothing else than the sample mean, but evaluated at those endpoints. So the sum of xi 1 to n, right? So you have n actually values that you have measured. You take those n values and you compute that sample mean. You sum over all of them and you divide by n. You get actually the realization of your sample mean, and 1 over that sample mean essentially will be the estimate of theta, right? So this would be actually the estimate of theta based on the method of moment estimator. Right? So one question we can ask ourselves is lambda hat biased, biased or unbiased estimator of theta? Right? So what would it be? Let's look at the expectation of lambda hat. This is expectation of 1 over this sample mean. Right? I can write this. Let's connect the two in a minute. 1 over the expectation of the sample mean, where those n random variables are exponentially distributed. Right? You remember the expectation of x when it's exponentially distributed is 1 over lambda. Right? So the expectation of x bar, the sample mean, will be still expectation of x, will be 1 over lambda. So this is equal to lambda. Right? We have done this. Those two, are they equal? You should know this by now. We have done this. They are not equal, right? Expectation of 1 over x is not the same as 1 over the expectation of x, right? So what you see here is that expectation of lambda hat is actually different from lambda. So this is actually a biased estimator. Okay, so you have here actually a formal methodology, method of moment, to build an estimator. But this estimator can give you, can actually be biased, right? So it is something that you have to know the properties of that estimator. Good, so this is actually one example where actually you have one parameter to estimate, lambda, right? So you don't need to, you just look at the first moment. You take the first theoretical moment, the sample moment, and you equate them. You can go to something a bit more complicated, where you have now a random sample, x1 to xn, but they're normal distributed, right? So you have a certain mean and you have a variance. And what we want to do is construct the method of moment estimator of mu and sigma square, right? So you have two estimators to construct here. So the first one, what can we do? We can look at the first moment. The first moment is expectation of x. This is mu, right? The sample moment here, so that's the theoretical moment. The sample moment is the sample mean, 1 over n sum 1 to n xi. The second moment is expectation of x squared, right? And you remember that the variance is equal to expectation of x squared minus the square of the expectation, right? So is expectation of x squared minus mu squared, right? So expectation of x squared will be equal to sigma squared plus mu squared, right? And what is our second moment here? Second sample moment is 1 over n sum 1 to n of xi squared. Right, so now we can equate them. So choose or construct those two estimators such that you equate those two, so you get mu hat is essentially equal to the sample mean. And here, the estimator of the variance plus the square of mu hat should be equal to 1 over at the second sample mean. Right, so from this, what you get is that the estimator is indeed equal to the sample mean, and the estimator of the variance is 1 over n sum 1 to n of xi squared minus the sample mean. Or in other words, you can write this as 1 over n sum of xi squared minus x times the sample mean. Okay, so this would be my method of moment estimator of sigma hat square, and this would be the method of moment estimator of the variance, right? And so here again, if you have data x1 to xn, you can compute those quantities here and get an estimate of mu and sigma square. Yes?
Why is it minus the sample mean and not minus the sample mean squared?
You're right, square. Good. Okay? Good. So is this biased, unbiased? So the first one, mu hat, right? We have that expectation of mu hat is expectation of x bar. This is the same as mu, right? So this is actually an unbiased estimator. Sigma hat square, what do we have here? Expectation of sigma hat square is expectation of 1 over n sum x1 square minus expectation of this. And so what we note here, what would it be this? This will be essentially n time expectation of x square divided by n minus expectation of the square of the sample mean. Expectation of x square is what we have here, right? So is rho square plus mu square. So that's rho square plus mu square minus the expectation of the square of the sample mean. Is this equal to 0? Mu square plus this? No, because mu is equal to expectation of the sample mean, but mu square is not equal to the expectation of the square of the sample mean, right? Mu square is equal to the square of the expectation, but it's not equal to the expectation of the square, right? So this is different from sigma square, and so this actually would give you a biased estimator of the variance and an unbiased estimator of the mean. Yes?
Go over how you went from expectation of 1 over n, the sum of xi, goes to n over n, expectation of x squared.
This one?
Yeah, that one there.
Right, so each of those here, so if you have expectation of 1 over n, sum xi squared, this is 1 over n, expectation of a sum of xi squared, right? This is 1 over n, sum of expectation of xi squared. Oops, sorry, right? So expectation of xi squared, we're all here, we have all those random variables here. They form a random sample. They're identically distributed, so they all have the same distribution that is equal to that, right? So expectation of xi squared, this will be essentially 1 over n, and here I have a sum over I to n of something that actually is the same for all of them, which is equal to sigma squared plus mu squared. Right? Right, so that's equal to n times sigma squared plus mu squared divided by n, that's sigma squared plus mu squared. Good? Good. So this is the first method. So you will see in the class with Bernie, you will have actually a few examples where you're going to play with this. Build method of moment estimator, and you can evaluate this on some real data. The second one I want to talk about is the maximum likelihood. So the maximum likelihood estimator. So there, what we're looking at, let's imagine you have a sample, and it could be a random sample, x1 all the way to xn with a certain distribution, right? It doesn't have always to be random. So in general, what you want to do there by maximum likelihood, you want to maximize a likelihood function. So what is a likelihood function? A likelihood function of a certain parameter theta is essentially the joint probability density function of those n random variable. And then here I'm stressing that actually is depending on a certain parameter that we want to estimate, right? So this is simply a joint PDF, could be PMF. And it's a function of a certain parameter that you want to estimate. So this, to stress the fact that the PDF is a function of a parameter, we call this a likelihood function. And so what we want to do is construct the estimator that maximizes this likelihood function. Okay? So this is called a maximum likelihood estimator. So let me show you again the two examples that we had earlier on, the exponential and the Gaussian. So let's have a random sample, x1 to xn, and they're all exponentially distributed, parameter lambda, and now what I want to find is the maximum likelihood estimator of lambda. Right, so how can we do this? I can take the likelihood function, which will be this joint PDF, but now actually it's a random sample, so actually all of them are independent. So what is the joint PDF here will be the product of each marginal, right? So that's product of lambda e minus lambda xi. Okay? They're all independent from each other, so the joint probability density function is simply equal to the product from 1 to n of x, xi. Right? So this is lambda n e minus lambda sum of xi 1 to n. This is lambda to the n e minus lambda n, right, where x hat here is 1 over n sum 1 to n xi. Okay, so what we need to do now is to find lambda that maximizes this quantity, right? And so rather than actually using the likelihood function, what we often introduce is the log of that likelihood function, which is called log likelihood function. And the reason why we do this is because the log is actually a monotonic function. So if you actually find the values of lambda that maximize this quantity, that value of lambda will be the same as the one that maximizes the log of that quantity, right? But this is easier because then you have n log lambda minus n lambda x bar. Right, so yeah. So how can we find this likelihood function? I want to maximize this quantity, so I want to find the lambda that maximizes this quantity. So I just hope that actually I have a concave function like this, L of lambda, as a function of lambda, and I can take the derivative and find the value of lambda that is such that the derivative is equal to 0, right? So if I take the derivative of lambda of L, I get n over lambda minus n x bar, right? And I force this to be equal to 0, so I find or construct estimator such that n over lambda hat is equal to an x, or in other words, lambda hat is 1 over x hat, right? So this is estimated, so the estimator is 1 over x hat, right? So 1 over the sample mean would be the estimator of lambda hat, okay? So here again, you get the same estimator as we had earlier on in the method of moment. The method of moment, and here the maximum likelihood gives you the same estimator, and this is again, this is a biased estimator, okay? So one more thing here that you have to be careful, you have to make sure that actually the derivative, you have to check that the second order derivative of this, right, this has to be negative, right? So you can check this at home. It's pretty straightforward. You have n over lambda, so it's going to have minus 1 over lambda square. And this is negative. That means actually, indeed, you have actually that log likelihood function is actually concave. And also when you take the derivative, the value, when you equate to 0, the value you're looking for is actually indeed a maximum and not a minimum. Okay? Good. So this is actually how you can actually construct the maximum likelihood estimator of, for instance, here, the random sample with exponential distribution. Yes?
So if we had other parameters in the PDF, for example, as we would in a Gaussian distribution, we would just treat those as constants.
That's what I'm going to do now.
Right.
Right? So, so if you have multiple, and you have to estimate multiple, you can actually extend exactly what we do here. You actually construct your joint PDF, you take the log likelihood function, and then you take a derivative with respect to each of those different parameters. And you try to find where actually your derivative is equal to 0. Right? So let's do that. So if you have, again, a random sample, x1 all the way to xn is normal distributed. And now what I want to find is the maximum likelihood estimator of mu and sigma squared, right? So this is a random sample, right? So they're all independent from each other. That means actually my likelihood function, and now it's a function of the 2 parameters I want to estimate. Here I was a function of only 1 parameter I want to estimate. Here I have 2. Is now what it is again, it's a random sample, so it's the product of the PDF of each random variable is Gaussian distributed. So what do we get is the product of 1 to n, 1 over 2 pi sigma square, minus xi minus mu square over 2 sigma square. Right? And so this is 1 over 2 pi sigma square n over 2. And here E minus, and I have a sum because of the product here. I have a sum from 1 to n xi minus mu square divided by 2 sigma square. Right? And here what we want to do is find mu and sigma square that maximize this likelihood function, right? So similarly to what we did with the previous example, let's look at the log likelihood function. So I'm looking at the log likelihood function, which is the log of this quantity. And what do we have here? If I do the log of this, I have minus n over 2 log of 2 pi sigma square minus the sum 1 to n of xi minus mu square multiplied by 1 over 2 sigma square. Right? And so same idea as before. Let's hope actually this is a concave function, right, in both mu and sigma square, right? So let's hope I have mu and I have this likelihood function, and I have something like this, and then I have sigma square, and I have also something like this. Right? So that's something we can actually have to check afterwards. So if we can, so we can take the first derivative with respect to mu. And what do we have here? The derivative with respect to mu, this is gone, right? And here what we get is minus a sum for 1 to n, xi minus mu 2, xi minus mu, multiplied by the minus. Here I'm going to have a plus divided by 2 sigma square. Right, so this is the 2 cancels each other. I have a sum of xi minus mu I from 1 to n divided by sigma square. And now I want to equate this to 0, so I choose such that this derivative is equal to 0. And so what do I get? I have sum 1 to n of xi is equal to n mu square. And so mu hat is 1 over n sum of xi is essentially x hat. Right? I have an n here because I have a sum of all the n's there, right? Right, so I have n. Right, so here I have actually my estimator, maximum likelihood estimator. Here is the sample mean. And I can take a second order derivative, right? If you take a second order derivative of this with respect to mu square, you have to find actually this is actually equal, is negative. So indeed you have this concavity. Right, so second one, what if we want to find the estimator of a sigma hat? What we can do is we take the derivative, but now with respect to sigma square. And what do we get here? The derivative with sigma square here is minus n over 2, 1 over sigma square, plus taking the derivative here with respect to sigma square, or minus here, minus sum 1 to n xi minus mu square, and I take a derivative with respect to sigma square, so I have sigma fourth, and I have a plus. Right, and now I choose sigma hat square such that this derivative is equal to 0. And so I have a mu that will become mu hat, that is the estimate I had from here. So what do I have is minus n over 2, 1 over sigma hat square, plus a sum of xi minus mu hat square over 2 sigma hat fourth has to be equal to 0. And so from here, what you get is sigma hat square is essentially 1 over n, sum from 1 to n xi minus mu hat, which is my sample mean. So I can write that actually my estimator is essentially equal to that. Right? Is that biased? Is that unbiased? This is biased. And this is what we showed last week. To make it unbiased, you would need to have n-1 there. Right? We did this last week. Okay, so this is actually an